Student, in this video, I am going to discuss about electric field due to an infinite line of charge. But before I start this topic, first I want to tell you about the linear charge density, surface charge density and volume charge density. Linear charge density is what? Charge per unit length, and it is denoted by lambda. So lambda is equal to Q by L and its unit is coulomb per meter. Similarly, surface charge density denoted by sigma, which is charge per unit area and its unit is coulomb per meter square. And third one is a volume charge density denoted by rho, and it is a charge per unit volume and its unit is coulomb per meter cube. And these charge density we will use to derive the expression for the electric field, which is based on application of the Gauss theorem. Now we derive the expression for electric field due to an infinite line of charge, which comes also under application of the Gauss theorem. And already I have given the first point under the application of Gauss theorem, derive the expression for electric field due to a point charge. And in this case, how can we find the electric field due to an infinite line of charge? Suppose this one is a wire and a charge Q is given to this wire. And when a charge Q is given to this wire, so that charge plus Q is uniformly distributed throughout its length, on its whole length. Let lambda be the surface charge density, be the linear charge density, linear charge density of this wire. So this one is a wire of infinite length and Q amount of the charge is given to it, and that charge Q is uniformly distributed throughout its length. And what we have taken here, lambda be the linear charge density of this wire. It means here lambda is equal to Q by L. Let P be a point at distance r from this. Let P be a point at distance r from it, where we want to find out the electric field. Dear student, remember this one is a not point charge. Here the charge is spread on a surface. It means here this charge is distributed on a surface, and for finding the electric field due to this one, we will use the Gauss theorem. So if our aim is to find the electric field at point P, then what is our first step? First we will draw a Gaussian surface which is passes to the point P and symmetrical to this line charge. It means we will draw a Gaussian cylinder coaxially and which is passes to the point P. So for this purpose, we draw a Gaussian surface coaxially around this one which passes to the point P. And in this way you will draw a Gaussian surface, means this one is a Gaussian cylinder and this one is Gaussian surface. And in the case of this Gaussian surface, this one is called plane surface. This one above one. This below one is also called plane surface. And this one is called its chord surface. Actually, the cylinder is like this. This one is a cylinder which is formed around this one here. And in this cylinder, this above one is called plane surface. This one is also called plane surface. And whole this one is called what here? Chord surface. And the electric flux will be passes through this plane surface which is at the top, plane surface which is at the bottom, and plane surface which is our chord surface around it here. So for finding the electric flux, first we will see here what the total electric flux passes through this surface. And for this purpose, you calculate the electric flux through this one, and through the bottom one. Suppose this one is, I am taking here surface 1, plane surface 1, P dot S means plane surface 1. This one is plane surface 2, and this one is chord surface, and I am taking this chord surface 3 here. It means for finding the total electric flux passes through this whole Gaussian surface, we will find out the total electric flux passes through the plane surface 1 plus total electric flux passes through this plane surface 2 plus total electric flux passes through this chord surface. So for this purpose, let us consider a small area element on this plane surface 1. Again, a small area element on plane surface 2, and again a small area element on this chord surface. And this one is a charge, line charge, and electric line of force due to this one is radially goes outward. It will goes radially outward because the charge is positive. So at this point P, electric field is outward, and the area vector of this small element will be also outward. It means electric field and the area vector of this chord surface both will be act in the same direction. But for this plane surface, here electric field will be act radially outward, and the area vector of this small element is normal to this surface and it will be goes outward. So this one is dA, and here the angle between vector E and vector dA is 90 degree. Similarly, here the electric field radially outward, and the area vector for this small area element dA is downward, radially outward. And now this angle is 90 degree. This angle is also 90 degree, but here the angle between vector E and vector dA is 0, means both are parallel. So for finding the electric flux through the first plane surface, what we will do? We will take electric flux passes to this small area element is vector E dot vector dA, and for finding the electric flux passes to this entire plane surface 1, what we will do? We will integrate it. So this will give electric flux passes through this plane surface 1, whole plane surface 1. Similarly, also you can find out the electric flux passes to this plane surface 2, and the electric flux passes through this chord surface. And for finding the total electric flux passes through entire Gaussian cylinder, we will add the electric flux through this plane surface plus electric flux through this plane surface plus electric flux through this Gaussian, means chord surface. So the electric flux through the entire Gaussian surface, means through the entire this Gaussian cylinder, we can find this electric flux phi E is equal to whole integration first vector E dot vector dA, and this one for plane surface 1. It means I am taking this plane surface 1, means total electric flux passes through this plane surface, plus electric flux passes through plane surface 2, means this plane surface, total electric flux passes through this plane surface, plus total electric flux passes through, means vector E dot vector dA for this chord surface. So here for chord. And for this plane surface 1 and plane surface 2, means for this above 1 and for this below 1, angle between vector E and vector dA is 90 degree. This one is also 90 degree. So here phi E is equal to, here we will write E dA cos 90, and vector E dot vector dA like E dA cos theta, and theta be the angle between electric field and area vector dA, plus similarly here E dA cos 90 means total electric flux passes through this plane surface 2 will also E dA cos 90 because the angle between vector E and vector dA is 90 degree. Plus here for curved surface this becomes E dA cos 0 degree because here vector E and vector dA both are parallel. So total electric flux, this phi E is equal to, cos 90 is 0, so entire this term becomes 0. Plus, here also cos 90 is 0, so entire this term will also become 0. Plus, cos 0 is 1, so you will get only whole integration E dA for this entire, you can say for this curved surface, curved area. Here A, you can write A here. So this phi E, this becomes here E, and this one for this curved area A dA. But remember this dA is the total curved area, means curved surface area of this cylinder, and curved surface area of the cylinder, as you know, 2 pi RL. So this phi E, this becomes E into 2 pi RL, since whole integration dA is equal to 2 pi RL for cylinder. The curved surface area of the cylinder is 2 pi RL. Suppose this is question number 1. It means by calculation here, phi is equal to E into 2 pi RL. Total electric flux passes through this Gaussian surface. And by Gauss theorem, total electric flux passes through a closed surface is equal to Q upon epsilon naught. And suppose this is equation number 2. From equation 1 and 2, from these two equations, because both is the electric flux passes through this Gaussian surface, closed Gaussian surface. So you can say E into 2 pi RL is equal to Q upon epsilon naught, or E is equal to Q upon 2 pi RL, and here epsilon naught. Or you can write here E is equal to 1 upon 2 pi epsilon naught Q by L into R. Same way, Q 2 pi epsilon naught LR, and here LR. And at place of this Q by L, this one is a charge per unit length, and at place of Q by L charge per unit length, you can write linear charge density lambda. So this becomes 1 upon 2 pi epsilon naught lambda by R. And here lambda is equal to Q by L, and already I have told you lambda is a linear charge density. So this one is what here? Electric field due to infinite line charge at distance r from it is given by 1 upon 2 pi epsilon naught lambda by R. In vector form, you can write here vector E is equal to 1 upon 2 pi epsilon naught lambda by R into here R unit vector, where R unit vector is a unit vector in the direction of R. So this one is electric field magnitude, and in vector form you can write this one also here. This is the expression for the electric field due to an infinite line charge. Look here. Here electric field due to infinite line charge is inversely proportional to R. Here 2 pi epsilon naught constant, and here linear charge density for a given wire is also constant. So you can say E is inversely proportional to R. So when you will draw a graph between electric field and R, so the nature is what here? E is inversely proportional to R. So the nature of the graph will comes like this. But from here you can say E is directly proportional to 1 by R. E is 1 upon 2 pi epsilon naught lambda. Suppose this one is a constant. And 1 upon R here. So you can say here E is directly proportional to 1 by R, or E is inversely proportional to R. So when you will draw the graph between E and 1 by R, so this one is a directly proportional. So the nature of the graph will come like this one. Be careful about these two graphs. So dear student, today you go through this derivation and also you look the graph between E, R and E versus 1 by R. In the next video, I will give the third application of the Gauss theorem for finding the electric field. Thank you.